When you deal with growth and decay problems, they're going to tell you in the problem that the rate of change of a variable is proportional to that variable itself. Or they may just say that this model follows the rules of exponential growth. If they say that in the problem, this is the formula that applies. So if you translate this directly, the rate of change of y with respect to time, dy dt, is, which is the equal sign, proportional to y means there's some proportionality constant k times the variable itself. You might also see this in population, dp dt equals the proportionality constant times the population itself. So why does this make sense? Well, let's look at the population and look at dB dt, its growth. If you start off with a population and there's only 6 people in a city, well, the rate at which that population grows is not going to be very fast. If you figure, each of the 3 couples have 1 kid a year, it's not growing very fast. Now, compare and contrast that to when you have a population with hundreds of people. This population is going to grow much quicker. So therefore, the rate at which it grows, the population growth, is proportional to how many people are there. The other way you'll see this is, say, in a pandemic, where the rate of change of people that are getting the disease varies proportionally with the number that already have it. If more people have the flu, then the rate that the flu increases in a given population is going to increase. Okay, now when you get these problems and it's simple, is proportional to y, we're going to end up using this formula down here. But I'm going to show you how to get from here to this formula, because sometimes it's not going to be this simple. Sometimes they're going to say proportional to the difference in temperature between an object and the ambient temperature. So in that case, you're not going to have this. You're going to have something like this. The change in temperature with respect to time is going to equal k times the temperature of the object minus the ambient temperature. So it's not quite as simple, and therefore the formula will be different. So I want to show you how to get from the standard situation to this formula. Okay, let's say we have a word problem that follows the rules of exponential growth. If they say that, then we could set up this equation here where the rate of change is proportional to the variable itself. So first we're going to go ahead and do separation of variables, and we're going to divide by y and multiply by dt. So we're going to have dy over y equals k times dt. We always want the dy or the dt in the numerator. Okay, and by the way, we'll be solving for y because that's in the numerator of this rate expression. Okay, so now we're going to integrate both sides. On the left, we're going to end up with the ln of the absolute value of y, and on the right, we're going to have kt plus a constant. We're going to do what I call whirly-bird, which is there's an understood base e here with that natural log. I'm going to take e to that equals the argument. So let's jump up here, and we're going to have now the absolute value of y, which is the argument in the whirly-bird maneuver, is equal to e to the kt plus c in the exponent. And be careful when you write that kt plus c that it all goes in the exponent. Don't let the plus c sneak down here. Okay, in this scenario, when you see the addition of exponents, that means that was at one point a multiplication problem. So we had e to the kt times e to the c. And now moving from right to left, if we were multiplying with the bases the same, we keep the base and we add the exponents. Well, now, since e itself is a constant of about 2.71, we could change this to c1. So let's rewrite this here in pink, that the absolute value of y now equals c1 times e to the kt. Okay, now if we want to remove that absolute value sign, we can, but we have to add a plus minus over here. And the final step in going from yellow to white is that this plus or minus C1 can be replaced with a C. So that is how you go from the original equation based on direct proportionality to this equation, which is going to be the equation that we use to solve these problems. In this first problem, we're told that the rate of change of y is proportional to y. So as soon as we see that, we can write this down, that the rate of change of y is proportional to y. And because we had that formula as such, we can jump to this, which is what we derived a few moments ago. Okay, so that's the formula we're going to be using. And the whole idea, folks, is to get the k and the c. Once you have the k value and the c value, you can answer any question they give you. So here, the way this works is, when t equals 0, y equals 2. When t equals 2, y equals 4. This is what we're going to use to get the c and the k. And once we have our equation with the c and the k filled in, it doesn't matter what they ask us. So let's go ahead and do that. So to get the c, usually that involves the initial condition. So if t equals 0, then this whole thing goes to 1. So we're going to have c times e to the 0, that goes to 1. So y is going to equal c. And they tell us that y equals 2. So if 2 equals c, then we know that the c is going to equal 2 for the rest of this problem. So let's go ahead and replace that c with a 2 that we obtain by setting t equal to 0. Now we're going to find the k. To find the k, we're going to use this second condition. So we're going to plug in y equals 4. Here's our 2. That's our c. E to the k, we don't know what that is, and the t equals 2. So we're going to solve for k. To do that, we're going to divide both sides by 2. We're going to have 2 equals e to the 2k. We're now going to take the ln of both sides, and when we take the ln of the right side, because the base of ln is e, when the base of the log matches the base of the argument, these cancel and you're left with the exponent. So now over here on the left in yellow, we're going to have ln of 2 equals 2k. Therefore, k is going to equal ln of 2 divided by 2. Now, when you get your k value, every teacher is different. The k value is very sensitive. Some teachers say you only have to bring it out to 3 decimal places. So let's use that technique for now. Our k is going to end up 3.347. But just so you know, if you're doing these problems and you have an answer key, if you only take it to 3 decimal places, your answer might be off by quite a bit because of how sensitive that k is. If you want to get relatively close to an answer key, you want to take this to 5 decimal places, and you can do your rounding at the very end of the problem. Okay, folks, now that we have our c and our k, the ball game is over. So here's going to be our equation. We're going to have y equals 2e to the kt, and we're going to use 0.347 times t. So now this question, what is the value of y when t equals 3? So right now we have 2 unknowns. We have the y, which is unknown, and we have the t that is unknown. And in these problems, they're going to give you one of these and ask you to find the other. So look what happens here. They give us t equals 3, and they ask us to find the y. So the y is going to equal 2e to the 0.347 times the t that they give us, which is 2. And when you do all that math, you're going to find that y equals 5.664. Next, we have this problem that discusses the population of wolves. So it says that the population is increasing at a rate directly proportional to this expression where the constant of proportionality is k. So folks, here we're going to have, I'm just going to use dp dt equal to constant of proportionality times this expression. Okay, we're going to be solving for p because the p is up here in the numerator. And let's see, we're going to, excuse me, multiply by dt and divide by 800 minus p. So that's going to give us 800 minus p equals k times dt. Okay, let's integrate the left side first, and we're going to use u substitution. So we're integrating both of these. We're going to let u equal 800 minus p, and du is going to equal -1 times dp. Therefore, dp is going to equal negative du. We're going to rewrite this integral as negative du over u. We're going to pull out the negative sign, and we're going to get this expression. And finally, when we take the natural log of u, we have our integral. And let's go ahead and back substitute. So we're going to have the absolute value of 800 minus p. Okay, that represents the left side of the equation. Now let's move to the right side. Here we're going to pull out the k, and we're going to integrate the dt like so. And that's going to give us k times t plus an arbitrary constant. Now we're going to multiply through by a negative, and we're going to change this to, here in white, ln absolute value of 800 minus p equals negative kt minus c, but we're going to, since it's an arbitrary constant, we could just change this to a c1, and that would absorb that minus sign. Okay. So now, folks, we have this situation, and we're going to go ahead and use Whirlybird here. There's your base e. We're going to go e to that equals the argument. So up here in pink, we're going to have e to the negative kt plus c1, being careful to put the c1 up top and not down here at the level with the e. Equals ln of absolute value of 800 minus p. Okay, rewriting this, I'm going to switch the order. I'm going to put this on the left side. Equals, this represents a multiplication problem. So this is e to the c1 times e to the negative kt. We're going to change e to the c1 to c2. E to the negative kt, and actually there is no natural log here, my mistake, that's the argument. Absolute value of 800 minus p equals this. Okay, now to remove that absolute value sign, we would have to multiply the opposite side by plus and minus, and we get the following. And now we could just change plus or minus c2 to yet another arbitrary constant. Let's just call it capital C, e to the negative kt. Okay, let's now proceed with the rest of the problem. Now, my recommendation when you have these problems and you have a negative in front of that p is to go ahead and plug in your initial values to get your c. And let me explain to you why. Okay, let's go ahead and do that. So at time equals 0, remember the variable that's on the bottom is going to apply to what's in the parentheses, and the variable on top is opposite the equal sign. Top, opposite the equal sign, bottom, what's in parentheses. So here we're going to have 800 minus 500 equals the arbitrary constant that we're trying to find, the particular constant, negative k times 0, and this is going to go to e to the 0, otherwise 1, and we're going to get a c value of 300. So that means our equation now changes to 800 minus p equals 300 e to the negative kt. Now, folks, for some reason, if you don't plug in here now, you're going to get a different c value if you try to solve for p and multiply through by that negative. Let me show you what I mean. So again, to repeat, if you have the negative in front of the p, go ahead and plug in now to get your c value. Do not do the following. Do not do this. Negative p equals c e to the negative kt minus 800, and then multiply through by a negative and change it to p equals negative c e to the negative kt minus 800, and then change that negative c to a positive c e to the negative kt minus 800. If you do that, and if you plug in now, p equals 500, c e negative k times 0 minus 800, 500 equals c times 1 minus 800, here you get c equals 1300, which is not the right answer for this problem. So I really can't explain why. If anyone can explain it to me and send in a comment, but I'm going to go ahead and advise that this is the stage that you plug in if you're dealing with a negative p there. Continuing on now for part B, if p of 2 equals 700, find the k value. So again, 700 is going to be the p, and the t is going to equal 2. So we're going to say 800 minus 700 equals 300 e to the negative k times t, and our t here is going to be 2. So here, folks, we're going to have 100 equals 300 e to the negative 2k. We're going to divide both sides by 300. We're going to get 1/3 equals e to the negative 2k. Okay, at this point, we're going to take the natural log of both sides. So the natural log of 1/3 equals natural log of e to the negative 2k. This is going to cancel out, and we're going to have negative 2k equals the ln of 1/3. Now, we can simplify that by saying negative 2k is going to equal the natural log of 1 minus the ln of 3. Natural log of 1 is 0, therefore we're going to have 2k equals ln of 3 when we multiply through the negatives, and finally k is going to equal ln 3 divided by 2. Okay, now that we have our k value and we have our c value, we can write this equation in green, that 800 minus p equals 300 negative ln 3 over 2 times t, and this equation will answer any subsequent questions that you might have on this problem. Next, let's move on to Newton's law of cooling, which states that the rate of change of temperature of an object is proportional to the difference between the object's temperature and the temperature of the surrounding medium. So here, this is a direct translation of these words into this equation. The rate of change of the object's temperature, that's right here, d temperature of the object with respect to time, is the equal sign, directly proportional, there's a k, to the difference between the temperature of the object and the ambient temperature, which is another way of saying the surrounding medium. So the way I remember that the O comes first as an object is TOA, which is similar to the Chief SOHCAHTOA acronym or mnemonic device to remember that the tangent is opposite over adjacent. Okay, now folks, this makes sense if you think about the formula. If you have a hot object, let's say the cup of coffee is 100 degrees, and you put it in a room that is hot, 90 degrees, there's not much of a difference between those two. So therefore, when you do the subtraction, you're only going to have 10 times K in terms of how fast it's going to cool. Now compare and contrast that to something like this, where you put a 100-degree cup of coffee in an absolute freezing room, 20 degrees. Well, now that difference is 80, so the rate is going to be 80K. Now, as you'll see in a minute, this formula as written is way too cumbersome. There's too many T's here. There's time, temperature of the object, ambient temperature. So what I recommend is that you take away this and change that to Y. We're used to seeing dy in the numerator and solving for Y. So we're going to change that to Y when we do these problems. In our first problem, we are told to let Y represent the temperature of the object in the room kept at a constant of 60 degrees. So that means our ambient temperature is 60 degrees. The object cools from 100 degrees to 90 in 10 minutes. How much longer will it take for the temperature to decrease to 80? Okay, so the first thing, as promised, is we're going to change that to Y and change that to Y. So our new and improved equation is going to be dy dt equals K times Y minus 60. Okay, folks, what we're going to do now is we're going to derive the working formula. This is our starting formula. This is the differential equation. So let's go ahead and do that. Let's separate the variables, and we're going to divide by Y minus 60 on both sides, and we're going to multiply by dt on both sides. Okay, we're then going to integrate both of these. On the left side, we're going to end up letting u equal Y minus 60. du is going to equal dy. We're then going to rewrite the integral as du over u. That du was, yes, that du was dy. And when we integrate that, we're going to have the natural log of the absolute value of u, and then we're going to back substitute and put back Y minus 60. Okay, as an absolute value. On the left side of the equation here, when we integrate that, we're simply going to get kt plus c. Okay, we're next going to do whirlybird with that base e, and we're going to say e to that equals the argument. So we're going to have the the absolute value of Y minus 60 equals e to the kt plus c, again being careful to put the c up in the exponent. Okay, let's make some room as we make our final adjustments here. Okay. All right. We are going to remove the absolute value signs, and when we do that, we're going to add a plus minus to the right side of the equation. We're going to change kt plus c to e to the kt times e to the c. Actually, let's do it the opposite. Let's keep the e to the c in front, like so. And then we're going to change this plus minus e to the c to simply c. Okay, now, folks, that predicament that we had in the previous problem with the wolves, where the p was after the minus sign, doesn't apply here. So you don't necessarily have to substitute right now, but I think this is a good time to do it. But you don't run into that problem when we had the negative in front of the p and you multiplied and you got the wrong answer. But let's go ahead and plug in our values right now to get our C value. All right. Sorry. Okay, so we are told now that initially the object is 100 degrees. So if we have an initial object of 100 degrees, that is our initial temperature, and the time at that initial temperature is going to be 0. So we're going to put in t equals 0 here, and when we do that, that's going to go to 1, and we're going to get a C value of 40. So let's go ahead and rewrite this equation. We're going to have y minus 60 equals 40 times e to the kt. And next, we're going to go ahead and plug in our second data point, and we're going to go ahead and figure out our k. Okay, now we have our equation with our c having been determined using the initial conditions with t equals 0. Our next endeavor is to find the k value. Folks, when you find the c and the k value, you can answer any subsequent question. Now, I've seen folks go ahead and move that 60 to the other side, but when you do that, make sure you don't forget to include that in the algebra. It's very easy to forget because most of the problems with growth and decay, you're just dealing with this term here. So I put it over there, but don't forget to include it in your math. Okay, so we're going to use this second data point that the object cools from 100 to 90 in 10 minutes. So that means at t equals 10, the object is 90. So we're going to go ahead and fill in, instead of t, we're going to put 10. I'm going to switch the order and make that 10k plus 60. Don't forget that plus 60. Okay, when we do our math, we're going to subtract 60 and divide by 40, and that's going to give us 30 over 40 equals e to the 10k. We're then going to take the natural log of both sides, and on the right side, because the base of natural log is e, when the base of the log matches the base of the argument, they cancel out, and you're left with the exponent. So we're going to take the natural log of 3 over 4, divide by 10, and when you do that, folks, you're going to get a k value of negative 0.029. Now, I'm only going to take it to 3 decimal places. Again, my answer is going to be a little bit off versus the answer key, but most teachers accept that to 3 digits. Okay, so now that we have our k value, now we can rewrite our equation as y equals 40e to the negative 0.029t plus 60. Now we can answer any question they throw at us. We have 2 unknowns. They're going to give us one of them, and we'll find the other. Okay, so here's their question that we will be able to handle. How much longer will it take for the temperature to decrease to 80 degrees? So what I'm going to do is I'm going to find how long it would take to decrease to 80 degrees, and then I'm going to figure out the how much longer aspect of the question. Okay, so we're going to decrease this to 80 degrees. That's now the temperature of our object. The question is, how long did it take to get there? So we are now going to solve for t. We're not going to forget that pesky plus 60. When we subtract 60 and divide by 40, we're going to have 1/2 on this side, and we're going to have e to the negative 0.029t. We're going to take the natural log of both sides. When we do that, these are going to cancel out. You're going to have the natural log of 0.5 equal to negative 0.029t. You're going to divide by negative 0.09t, and you're going to get t equals 23.9 minutes. Okay, let me just review that. So we're going to have the ln of 0.5 in your calculator equals negative 0.029t. So whatever this value is in your calculator, we're going to divide it by negative 0.029, and indeed that is going to be a negative value. don't forget, here is the graph of the natural log function. It has a vertical asymptote at x equals 0, and it stays negative until it reaches 1. So at 0.5, you're going to have a negative value, and when you divide by that negative k value, you're going to get a positive time in your answer. Okay, so now we know, let's just do a little diagram here. We know that from 0, time equals 0, it takes 23.9 minutes to get to 80 degrees. And we know that it took 10 minutes to get to 90 degrees because they told us that. So basically, they want to know how much longer it takes to get to 80. So that's this distance right here, that time difference. So if you do 23.9 minus 10, the final answer to this is 13.9 minutes. In our next Newton's law of cooling problem, we have a roast that is taken out of the oven with a temperature of 185 degrees. It's put on a counter in a room that is kept at 75 degrees. What is the differential equation that matches this scenario? So recall, Newton's law of cooling is that the rate of change of the temperature of an object with respect to time is directly proportional to the difference between the temperature of the object and the ambient temperature. Remember the mnemonic TOA. The object comes first. Folks, this is way too many T's. So we change this to dy, which we're used to seeing in the numerator. Y representing the temperature of the object is going to be K times Y minus the temperature of the ambient temperature, or that of the room. And in this particular problem, the temperature of the room is 75 degrees. Okay, so this is the initial differential equation. Now, there's subsequent questions here that is going to mandate that we solve this differential equation and get a working equation. So we're going to divide both sides by y minus 75 and multiply both by dt. We're going to end up on the right side with dy over y minus 75 equals k times dt. When we do u substitution on the left side, we're going to end up with du over u, and the integral of that is going to be the natural log of the absolute value of u. So we're going to just go ahead and jump to that, and we're going to have kt plus c on the right side. We're going to do whirly-bird, and we're going to end up with e to the kt plus c equals the absolute value of y minus 75. Okay, let me make some room and talk about how to proceed from here. Okay, so now in order to remove that absolute value sign, we're going to put a plus minus over here, and we're also going to change this to e to the kt times e to the c, because that's what would result in the addition of the exponents. So let's do that all in one fell swoop. We're going to have y minus 75 equals plus minus e to the c times e to the kt. We're going to condense that to its own constant, and we're going to end up having this formula here. Y minus 75 equals c e to the kt. Now, folks, if this was a problem where that minus sign is in front of the variable, you would go ahead and plug in your initial conditions here to get c. What you would not do is put the constant on the other side and then multiply through the negative. Okay, let's go ahead and solve for y formally. So we're going to have y equals c times e to the kt plus 75. Okay, to get our c value, we need to plug in the initial condition of t equals 0. So at t equals 0, we know the temperature of the roast when it's pulled right out of the oven is 185 degrees. This is going to be c times e to the k times 0 plus 75. K to the 0 is 1. So we're going to end up with C being 185 minus 75 equals C. C is going to equal 110. So now we can rewrite this equation, the working equation, as y equals 110 times e to the kt plus 75. Now, our next endeavor that will allow us to solve any of the subsequent questions is to find that k value. So we're going to use this second piece of information, that the temperature of the roast is 150 degrees after 30 minutes, to find the k value. Okay, now that we've used our initial conditions to find that particular C, we're now going to find the K. To do that, we're going to use this data point here, that the temperature of the roast is 150 degrees after 30 minutes. So the Y is going to be 110, e to the K times 30 minutes. We're replacing 30 for T, plus 75. Folks, don't forget that pesky plus 75. Most of these exponential growth and decay problems only involve this term, but don't forget to subtract that 75 before you do anything. Okay, so we're going to subtract 75 from both sides, and then we're going to divide by 110. We're going to end up with 75 divided by 110 equals e to the 30k. We're going to go ahead and take the natural log of both sides. Here, these are going to cancel, and you're going to get 30k equals the natural log of 75 divided by 110. Folks, when you do that, you plug that in the calculator and divide by 30, you're going to get a k value is going to equal negative 0.0127. Okay, so now our new and improved equation is going to be that the y value equals 110 e to the negative 0.0127 times t plus 75. Okay, now that we've found our particular C value and our K value, we can answer any question that they give us. Look, there's two unknowns, the Y, which is the temperature of the object, and the time. They're going to give us one of them and ask to solve for the other. Okay, here it is. What is the temperature after 45 minutes? So that means we're trying to solve for Y, and they're giving us the time. So folks, we're going to plug in 45 for time here. We're going to multiply this, take e to that, do all our math, and when we do that, we're going to get a temperature of approximately 136.93 degrees. Okay, for part 2, when will the roast have cooled to 100 degrees? The fact that they're asking for the word when, that means they want the time. They're giving us the temperature of the object. So we're going to have 100 equals 110 e to the negative 0.0127t plus 75, and we're trying to solve for t. We're going to subtract 75 on both sides and then divide by 110. That's going to give us this, e to the negative 0.0127t. We're then going to take the ln of both sides. When we do that, these cancel out, and we're going to end up taking the natural log of that fraction, dividing by negative 0.0127, and your final answer is going to be a time, of 116.06 minutes. Next, we are told that a population grows continuously at a rate of 1.85%. How long does it take for the population to double? Okay, so you see that it's growing continuously. That means we're going to be dealing with exponential growth. And when they tell you that the rate is 1.85%, folks, that is your K value. So because this is a standard problem, where it's just going to be directly proportional to the population, we can jump right to this formula that the y is going to equal c e to the kt. Now we know the k, okay, so it's going to be c e to the 1.85%. We're going to take away the percent symbol, and we're going to divide by 100. When you divide by something, it gets smaller. So that means we're going to move this decimal place 2 times to the left because there's 2 zeros in 100. So the k value is actually going to be here, 0.0185 to the t. Okay, now the question is, how are we going to find our c value here? Unlike in many problems, they don't give us any initial conditions. Okay, we're going to use this, the fact that they tell us that the population doubles, or they're asking us when does the population double. So that means if this is the initial population, let's call that C initial, or O as in original, this has to be 2 times that. That's what doubling, it's exactly what doubling means. So because it's the same variable, you can cancel those out. So now we have this equation, 2 equals e to 0.0185t. We're going to take the natural log of both sides, and we're going to end up with the natural log of 2 being equal to 0.0185t. And when you do the math, you're going to get that the time is 37.467 years. Folks, I want to point out something about the problem we just did, where we found that the time is 37.47 years for the population to double. If you see this rate of growth here of 1.85%, you might be tempted to use this formula, where the amount at times t equals the initial amount times 1 plus or minus r raised to the t, where r is the decimal version of the growth rate. So here we have 1.85%. Again, we're going to divide that by 100. So it starts here, the decimal place, it ends up here. So this is going to end up being 1 plus 0.0185 raised to the t. Raised to the t. And we're going to end up with 2 times the initial amount, because that would reflect a doubling. So again, the a sub zeros are going to cancel out, and you're going to take the natural log of both sides. So you would have natural log of 1.0185 raised to the t. You can pull this out, and you're going to have t times the ln of 0.0185. And when you divide ln of 2 by the ln of 1.0185, I did that here on Desmos, and lo and behold, you get 37.8 years. So that is not appreciably different than what we just had. But the fact that you see the word continuously here, to me means you should use the formula that we used, which was that y equals c e to the kt, and you're going to use this as your k, but again, converting it from the percent to the decimal form for k. Next, we are told that we have $1,000 deposited with a 4% interest rate compounded continuously. So whenever you see the word continuous, you're going to use this equation. E has to be involved. Okay, so now we are given an initial amount this time, which is 1,000. We're going to have E, the K is going to be 4%. So again, we're going to have 4%. That means 4 divided by 100. Your decimal place starts here. It moves over twice. So that's going to be 0.04. The time is 8 years. So folks, when you do that math, you're going to get a total of $1,377.13 as your final amount